Hello everyone. Let's continue topic dipole. In the last video, we saw what is the amount of electric field due to a dipole on its axial point. In this video, we are going to discuss what is the electric field due to a dipole on the equatorial line. First thing that we will have to understand what is the meaning of equatorial line. Let me draw a dipole. A dipole of plus and minus 2 charges, and distance between them is 2a. This is the direction of dipole from minus to positive charge, and let the center be O. So from the middle point of the dipole, if we draw a perpendicular, that is called equatorial line. This line is called equatorial line, and on this given line, any random point will be known as equatorial point. Our task is to find the amount of electric field due to this dipole on any of the given points, which will be on the equatorial line. Let a point P. Our task is to calculate the electric field at point P. This is our target. So due to this plus Q charge, electric field will be outward. That I am writing E plus. And due to minus charge, electric field will be inward. That I am writing E minus. Let the distance between OP R. In order to solve two vectors, we will have to use our vector addition method. First, if we look at the figure, we will get to know that the angles are 60, 60 and 60. So that is why this angle will be 120 degree. But first of all, let's make component. Let's resolve this vector E plus into two components. So this component will be, as this angle is 60 degree, so this angle will also be 60 degrees. So that is why this will be E plus cos theta or cos 60 degree. Similarly, another component, this component will be E plus sin theta. When we will resolve this E minus, then this angle is 60 degree. This angle will also be due to alternate angle 60 degree. Ultimately, these two lines are parallel lines. So this one is 60. This one will also be 60 degree due to alternate angles. So this can be said as E minus cos theta, and this component will be E minus sin theta. This distance is R. As these two are the mirror elements, they will cancel out. Let me draw this figure again. Okay, this is hypotenuse. This will become r square plus a square. Electric field due to plus q charge at point P kq divided by r square, this distance square. And electric field due to minus q charge at point P, now as these two components are in the same direction on the same line, so in order to find out the resultant we will have to add these two components. So the resultant at point P would be uh, EP is equals E cos theta plus E cos theta. Cos theta is common. Now let's substitute the values of E plus and E minus from these equations. So I'm writing it as E plus from here, and I will remove this root from a square, so it will be directly KQ divided by R square plus A square plus KQ divided by R square plus A square into cos theta. Is it visible? Now fine. So let's solve these two. So 1 plus 1, 2 times KQ divided by R square plus A square into cos theta. 2 times KQ and on the place of cos theta we can write base upon hypotenuse. Base upon hypotenuse. Base upon hypotenuse. So this becomes 2k, rather I would write it as k q into 2a divided by r square plus a square r 1 plus half 3 by 2. If we let this distance r much greater than a, let me erase this side. If we assume r is much greater than a, so we will write EP is equals 2 times, not 2 times, k q 2a divided by r square, and this a square quantity will be negligible. So a square, sorry, r square multiplied by 3 by 2. So here we will have r cube. So this is the value of electric field on the equatorial point P due to a dipole. So I am writing it as E equatorial. So this is the final formula. In order to represent this formula in vector form, so I will write it as E equatorial, vector E equatorial equals K Q 2A divided by R cube, and as it is very clear from the figure also, resultant is in opposite direction from the direction of the dipole. Direction of dipole is leftward and direction of dipole is rightward. So minus sign. So this is the electric field due to a dipole on the equatorial point P, that is K Q 2A divided by R cube. Let me again make it very clear. The direction of the electric field, direction of electric field is rightward and direction of dipole is leftward. So that is why I am writing E vector and P cap with negative sign, just to show that the directions are opposite. Now the next topic is electric dipole moment. See, electric dipole is some, as we have discussed in the last video, that a dipole is nothing but a combination of two pair charges of equal magnitude and opposite sign. When two equal and opposite charges are separated by a small distance, that arrangement is called electric dipole. But the strength of electric dipole is measured in terms of electric dipole moment. This is a new quantity that will be defined as any of the two charges multiplied by distance between them. Suppose these are the two, suppose this is the dipole, this is our dipole. Dipole moment that I am writing small p will be equal to q times 2a. This is what we call electric dipole moment, and its unit will be coulomb meter. So electric dipole moment is the product of any of the two charges multiplied by separation between them, that is 2. So this is what we call electric dipole moment. That's it. As per this formula, if you want to represent the electric field on the equatorial point and on the axial point, you can also represent them in terms of electric dipole moment. What was the electric field due to the axial point? Electric field on the axial point due to a dipole was, that we have considered equation number 1 was something like E axial equals r cube. So this term in equation number 1 can be replaced by a new term called P, that is electric dipole moment. So the final formula for axial would be 2kp divided by r cube. Similarly, electric field on the equatorial point, k q into 2a divided by r cube. This is the second formula. So this term q into 2a can be written as P. So E equatorial is kp divided by r cube. Now let's discuss the next topic, that is electric dipole moment. Now the next topic that we are going to discuss is what will happen if we keep a dipole in a uniform electric field. Dipole in a uniform electric field. Let's suppose, let me draw a uniform electric field. Here is the uniform electric field lines. This is a dipole. These are the charges plus Q and minus Q. Let the dipole is aligned at theta angle from the electric field. What is theta? Angle between dipole and electric field. Direction of dipole is from negative to positive charge. From the formula of electric field E is equals to F by Q, we can calculate F is equals to E into Q. As these are the electric field lines outward in the rightward direction, so on the plus Q charge there will be an electrostatic force of repulsion that will be outward also. And on this plus Q charge, electrostatic force will be in the left direction. Let the separation between the charges is 2A, that I am writing A plus A, that is 2A. So there is a formula in class 11 that is nothing but torque, that is called F multiplied by perpendicular distance. Torque is turning effect of force, or tau. Tau is defined as force multiplied by perpendicular distance. So if we want to write F in terms of QE, that is also correct. So we can replace it by QE, rather vector QE. Multiplied by perpendicular distance. Perpendicular distance between the two charges is, if we resolve this, then we will get to know that this particular component is E cos, A cos theta. Similarly, here also this component will become E cos theta, and these two components will cancel out, because this component is also ultimately A cos theta, so they will cancel out. So I'm not writing them. But another component that will be A sin theta, and here also A sin theta. So A sin theta plus A sin theta will become 2A sin theta. So let me write it as 2A sin theta. This is the distance, perpendicular distance. I can make an adjustment. Q into 2A into E sin theta. So this can be written as P, that is ultimately vector dipole moment, Q into 2A. So P E sin theta barabar torque, tau. So this tau can be written as vector E cross vector E. Both formulae are correct. Direction of torque. If electric field lines and force, electrostatic force of repulsion, both are lying in the same plane, so the direction of the torque will be from the outward from the board or inward from the board perpendicularly. Both are correct. As per the figure, if we want to find out the correct direction of the torque, so we can say that direction of torque will be where is our direction of P? This is the direction of P. So direction of P is something like this, and direction of F is in rightward direction. So P multiplied by F. So the direction of the torque will be in outward direction.